In this video, we'll take a look at some of the characteristics and properties of an audio signal. This means that we are finally leaving the physical domain of sound as perceived as pressure waves into the analog domain where sound is represented as voltage-varying audio signals. We tend to use the term sound and audio indiscriminately, but what's the difference here? Sound is a pressure disturbance in a physical medium, like air, that can be perceived by hearing. That doesn't necessarily mean that sound has to be audible. Infrasonic and ultrasonic sounds are below and above the normal range of human hearing, but these are sounds nonetheless, imperceptible disturbances in a physical medium. Audio, on the other hand, is an electrical or digital representation of sound. An input transducer, such as a microphone, is needed to convert sound into audio. The audio signal itself cannot be perceived by hearing. It's just an electronic representation, and thus for it to be audible, the audio signal would have to be converted into sound using an output transducer such as a loudspeaker. We won't get into the details of physical to analog conversion of sound to audio and how transducers work. We'll just assume that we're given an audio signal to work with. Electrical audio signals are analogous to acoustic signals or the pressure waves that it was recorded from. A transducer basically maps the changes in pressure of a wave to changes in the potential difference or voltage of a signal. The amplitude values of the signal represent the different voltage levels, and they are usually bidirectional alternating signals with a steady state of 0 volts. When we study the signal's amplitude over time, or generally ask the question, how large an audio signal is, we have several characteristics which define the signal. To discuss these, we'll take a very simple audio signal, the simplest of them all, the humble sine wave. There's an entire module dedicated to sinusoids and what they are if you want to learn more. But we'll stick to sine waves because it's the simplest and purest form of an audio signal. The peak value determines the instantaneous maximum amplitude value within one period of a signal. The peak value can also be the maximum value that is ascertained during any period under consideration, even though the usual designation here involves the maximum value within one period. Usually, the peak value measurements is used in symmetric signals, signals that deviate equally far away from zero in both the positive and negative directions. In practical audio engineering, particularly for recording and transmission of audio signals, it's the peak-to-peak value that is significant. This value describes, so to speak, how much space or voltage range the signal takes up in the electrical circuit. Also, the peak-to-peak value indicates how much a membrane must move in a purely physical sense from one extreme to another in order to reproduce the sound. For a sinusoid, the peak-to-peak value is just twice the peak value. No difficulty there. But in the real world, acoustic signals contain a lot of asymmetry. The voice, for example, or musical instruments like a percussive instrument's impact can be highly asymmetric. The average value is based on the average of the numerical values of the amplitude of a signal over a period. How would you calculate the average? Well, you sum up a set of values and you divide it by the number of values is summed up. Quite simple, right? So let's see how we can actually mathematically express this for signals. You have a signal, let's say f of t, which is a function of time. This function could be a simple sine function over time, like so. Let's add all of the values of this sine function over the duration of its period. So let's say that this function completes exactly one period in t seconds. We need to add up all of the values of this sine function within this period. How do we do that? This is a continuous function after all, and there are infinitely many points within this period of time to include. So we need to use integral calculus as a tool to calculate the sum of the values within this period. So we integrate f of t with respect to time t over the range of 0 to capital T, which is the period. This gives us the sum. So we just need to divide this by the period itself, and that gives us the average. Obviously, this formula doesn't make much sense if you can't visualize what's happening. So let's use a graphing calculator to visualize every step that we just took. That'll lead us to the average. I'm going to use Desmos here, and you can check out the link below to play with the calculator with all the values filled in. So let's start off with a sine function, f of t equal to sine t. Here, you get the familiar sine function that we know and love. Let's consider the x-axis here as the time axis, t. The sine function here starts from its period of 0 and ends somewhere at around 6.28. This is in fact the value of 2 pi. And it makes sense if you've seen the module on the origins of the sine wave, that the sine wave's period is 2 pi radians. Now we know what the period of the sine wave is. It's 2 pi. So let's establish that. Let's now integrate over the range of the period. So I'll sum up f of t with respect to t over the range of 0 to t, which is 2 pi. Now you can already see a problem here. The result that you get is 0. That's because the sine wave is exactly symmetrical across the amplitude axis. And you get a peak in the positive amplitude axis and a trough in the negative axis. Since it's symmetrical, the positive and negative values cancel each other out. Effectively, the sum and in turn the average is 0. The result of 0 doesn't make a lot of sense. The average value of a sine function cannot be 0, it's doing some work. And besides, the positive and negative axes are just frames of reference. So hence, to avoid this problem, we take the absolute value of the function instead and discard the sign. Let's see what the sine function looks like when we discard the sign and take the absolute value of the function. It's sort of like a bouncing sine wave constrained to the positive axis. If we now take the sum of this function, we get a value like this, where the sum is the value of 4. Though this may look like a function, with it being represented as a straight line on a graph, it's a single scalar value, since we are reducing the sine function by summating it and removing the reference of time. Now we can divide this by the time period, and that'll give us the average of around 0.636 for a sinusoidal function. The discussion carries on in the next video. The average value calculations, though I've described it here, is rarely ever used in audio signal measurements. The generally and widely used metric for measuring the average of a signal is called RMS value, or root mean squared value. Since it's quite important to understand the significance of the RMS value, why it's used and what it means in the context of audio signals, I've dedicated the whole of the next video for that. I'll see you in that one.